The world of astronomy is experiencing a period of intense discoveries, and updates about 3Y Atlas have been arriving daily, keeping the scientific community in a constant state of alert. The question echoing among researchers around the globe is singular. Is 3Y Atlas breaking apart? This question gained urgency after the November 9th observations, which revealed unprecedented aspects of this interstellar object. The data documented material jets extending considerable distances through space, presenting characteristics that suggest possible ongoing fragmentation. The international scientific community is divided between fascination and perplexity in the face of these unprecedented observations. Observational data shows that jets directed toward the Sun reach approximately 1 million kilometers in length, while those oriented in the opposite direction extend nearly 3 million kilometers. Considering that the Earth-Moon distance corresponds to about 400,000 kilometers, these jets represent a magnitude 7 times greater than this familiar orbital reference. The temporal evolution of this phenomenon presents characteristics that intensify the fragmentation debate. Hubble Space Telescope observations in July recorded only a discrete luminous cloud surrounding the object. The jets documented on November 9th demonstrate dimensions 3,000 times greater than previous Hubble observations, indicating a significant transformation in a relatively brief period. The fragmentation hypothesis gains credibility when we examine historical precedents in astronomy. The case of comet Shoemaker-Levy 9, discovered in 1992, offers a relevant example for the current discussion. This object experienced fragmentation after excessive approach to Jupiter, resulting in its division into 21 distinct components due to the planet's gravitational forces. The subsequent events of July 1994 provided valuable scientific observations that inform our current understanding. Each fragment of Shoemaker-Levy 9 impacted Jupiter, generating atmospheric disturbances of sufficient magnitude for terrestrial detection. The resulting marks from these impacts exceeded terrestrial dimensions and maintained visibility for prolonged periods. Comet Holmes presents another case that fuels the fragmentation debate. In 2007, this object manifested a sudden increase in brightness, accompanied by the formation of an expanding nebulous structure. Both Shoemaker-Levy 9 and Holmes represent examples of natural comets subjected to fragmentation processes, offering potential parallels for the current behavior of 3Y Atlas. To adequately contextualize speculations about fragmentation, it's worth reviewing typical comet behavior. Traditionally, these objects develop a main tail that orients in the direction opposite to the Sun, resulting from solar wind action. This phenomenon functions as a propulsion mechanism that displaces gases and particles at speeds exceeding 1.3 million kilometers per hour. The presence of jets directed toward the Sun in 3Y Atlas constitutes a significant anomaly that feeds fragmentation theories, as these must overcome solar wind resistance to maintain their structure. The ability of these jets to preserve their cohesion across millions of kilometers suggests considerably elevated density and intensity properties, possibly resulting from multiple active fragments. Although anti-tails represent relatively rare phenomena, precedents exist in astronomical literature. Avi Loeb's quantitative analysis reveals fundamental discrepancies in mass loss calculations that significantly strengthen the fragmentation hypothesis. His estimates indicate that 3I Atlas is expelling approximately 50 billion tons of material monthly. The determination of space object mass is based on analysis of their orbital trajectories and solar gravitational influence on their movements. Through these methods, researchers calculated that 3I Atlas possesses a total mass of approximately 33 billion tons, creating a mathematical paradox that intensifies the fragmentation debate. This configuration presents a fundamental contradiction that many scientists interpret as evidence of fragmentation. An object with a mass of 33 billion tons cannot, theoretically, expel 50 billion tons of material. This inconsistency requires explanations. Trustee. that transcend conventional models of cometary behavior, directing attention to structural disintegration processes. Historical precedents offer support for the fragmentation interpretation. During the disintegration of Shoemaker-Levy 9, the total amount of material released significantly exceeded initial estimates of the original comet's mass. This apparent contradiction was subsequently clarified through understanding of fragmentation processes, offering a model for interpreting current 3-1 Atlas anomalies. The fragmentation mechanism in comets involves differential solar heating, a process that could explain 3Y Atlas's current behavior. Solar radiation does not uniformly heat icy objects. The solar-facing side experiences elevated temperatures, while the opposite side remains significantly cooler. These thermal gradients generate internal structural tensions that accumulate progressively. The accumulation of these tensions can exceed the material's cohesive resistance, resulting in sudden structural rupture. This process resembles the behavior of vitreous materials subjected to excessive pressures, producing catastrophic fragmentation that many researchers believe is occurring with 3I Atlas. Fragmentation exponentially multiplies the surface area exposed to solar radiation, a mechanism that would perfectly explain current observations. The increase in available surface allows simultaneous sublimation of larger ice volumes, generating substantial quantities of expanding gases. This process explains how objects can apparently lose material in quantities exceeding original mass estimates. If 3I Atlas has effectively fragmented into multiple components, this condition would adequately explain both the 7 jets observed on November 8th and the extensive structures documented the following day. Each fragment would contribute individually to material ejection, resulting in the total quantities calculated by Loeb and supporting the active fragmentation hypothesis. However, a fundamental uncertainty remains that keeps the scientific debate alive. Definitive confirmation of 3I Atlas fragmentation has not yet been established. This question has significant implications for our interpretation of the observed phenomenon and continues generating intense discussions in the astronomical community. Should future observations demonstrate that the object maintains structural integrity while continuing to produce high-velocity jets, we would be confronting an unprecedented phenomenon in astronomical literature. Such a discovery would represent the first known object that doesn't fit established patterns, violating fundamental principles related to mass conservation and challenging our current understanding. Beyond possible fragmentation issues, 3I Atlas presents distinctive orbital characteristics that add complexity to the scientific debate. Its trajectory classifies as retrograde, a movement pattern that contrasts significantly with the predominant orbital dynamics in our solar system. Visualizing this orbital anomaly requires adequate perspective. Observing our solar system from an elevated position above Earth's north pole, all major planets follow consistent counterclockwise orbits around the Sun. This directional uniformity constitutes a fundamental characteristic of solar system architecture. 3I Atlas, however, follows a clockwise trajectory, opposite to the movement of virtually all other significant system objects. This orbital configuration occurs in only 1 to 2% of known objects, being more common in small moons captured by planets after initial system formation, adding another intriguing element to the debate about its nature. The identification of a large interstellar comet in retrograde orbit constitutes a statistically improbable event that intensifies scientific speculation. Additionally, 3I Atlas's trajectory aligns remarkably with the ecliptic plane, the planar region where major planets orbit. This geometric configuration presents reduced statistical probabilities that fuel diverse theories. Interstellar objects typically arrive from arbitrary directions, frequently at sharp angles relative to the ecliptic plane. 3I Atlas's nearly perfect alignment with this plane represents a probability of approximately 0.2%, or 1 chance in 500. This convergence of statistically improbable factors evokes comparisons with Oumuamua, another interstellar visitor that generated similar debates in the scientific community. Oumuamua demonstrated an apparently elongated shape, unusual brightness variations during rotation, and an inexplicable acceleration when leaving the solar system. Oumuamua's anomalous acceleration could not be adequately explained through conventional outgassing, leading Avi Loeb to propose alternative hypotheses in his work dedicated to the object. Loeb suggested that Oumuamua could represent artificial technology, specifically a solar sail propelled by radiation pressure, generating controversies that echo in the current debate about 3Y Atlas. The astronomical community maintains diverse perspectives on these interpretations, with many researchers favoring explanations based on unusual composition, possibly hydrogen or nitrogen ice, that could explain observed behaviors. The scientific debate continues without definitive resolution, but the 3I Atlas case adds a new dimension to these discussions. An important distinction separates Oumuamua from 3I Atlas: their dimensional scales. Oumuamua presented relatively modest dimensions, possibly a few hundred meters in length. 3I Atlas, in contrast, is more than 1.6 kilometers wide and has a mass of billions of tons, making any potential fragmentation process more dramatic and observable. The identification of an object of this magnitude in such an unusual orbital configuration naturally raises deeper questions about origin and nature. Individually, the large size and retrograde orbit may not constitute conclusive evidence, but their combination with mass loss anomalies creates a set of characteristics that keeps the scientific community in a constant state of alert. The convergence of these multiple anomalies, unusual directional jets, paradoxical mass loss, retrograde orbit, and ecliptic alignment, establishes 3I Atlas as one of the most intriguing objects in contemporary astronomy. The fragmentation hypothesis offers the most plausible explanation for these observations, although definitive confirmation is still necessary to resolve the current scientific debate. Daily updates about this object keep the international astronomical community in constant expectation. Each new observation may provide crucial evidence to determine whether we are truly witnessing the fragmentation of an interstellar visitor or confronting a completely new phenomenon that will challenge our fundamental understanding of space objects. Regardless of the final explanation, this object will certainly contribute to expanding our understanding of interstellar visitors and the limits of known natural phenomena. To follow daily updates about this and other developing astronomical mysteries, consider supporting this channel through likes and subscriptions, ensuring access to the latest discoveries that are shaping our understanding of the cosmos.